Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tare, and this is my continuing feature on the Math Lovers book. I'm on section 3.4 of volume 1, which is on Fibonacci numbers and the golden ratio. And this is my sixth video on this section. Today I'm going to talk about important application of the golden ratio, namely the pentagram. Anyway, let's begin. So, in case you guys don't know, the pentagram is just another name for the familiar five-pointed star, the one that appears on the American flag, 50 of them, as a matter of fact. Um, and it's composed of five line segments. If you like, it's a self intersecting. I guess you might want to call it an irregular polygon. Polygon where the line segments that made it up can intersect themselves. Those are considered polygons too, but they're irregular polygons because they intersect themselves. And the pentagram is an example of one. As a matter of fact, it's probably the simplest example. And this is the regular pentagram. And what does the golden ratio have to do with a pentagram? So you'll notice that there are four different length line segments that make up the pentagram, and I show them here in different colors. The longest ones are black. That would be the kind of the side length of the pentagram, if you like. These long, I don't know what you call them. I guess chords of the circle that makes them up, which are almost as big as the diameter. But then you've got, another line segment shown in um, green. Oh yeah, the red one. Actually, forget about the black ones. The red one shown. There's four different colors. There's red, green, blue, and violet. And the red one is the longest of the four colored ones. That has, if you like, we can call that L. If we call the shortest length L. So L is the purple one. That's the length of the short line segment that comes between two big ones that make a 36-degree angle, forming that small wedge, the one on the lower right. And if we call that length L, then the next shortest is the blue one that has length phi times L, where phi is the golden ratio. So that one's exactly phi times as long as the purple one or the violet one, if you like. And then we got the green line segment, which is phi squared times L. And you can actually see the algebraic relationship satisfied by the golden ratio if you do that. Yeah, notice you have a golden section here. The green line segment is composed of a line segment that has the same length as the purple segment. That would be the shorter part, the shorter partition. And then the longer partition is the one that's congruent to the blue line segment, which I said was phi times L. So we have L plus phi times L equals phi squared times L. So that's just the golden section. Pretty neat. And then finally, the last one, the red one, that's the longest line segment in this pentagram. This has length phi cubed times L. And I think you can see once again that this satisfies the same definition of the golden ratio given by the golden section, because notice that it's actually made up of three line segments, but we can think of them as two. The one on the left, if you combine the two line segments on the left, making up the red line segment, this is congruent to the green one, which has length phi squared times L, and then the remaining piece has length phi times L. That's congruent to the blue section. And I said the whole thing is phi cubed times L. Well, yeah, because phi cubed times L is phi L plus phi squared times L, which is equivalent to phi cubed equals phi times phi squared, which I think you can see is just the relation we had for the golden section. We multiply everything by phi, because phi squared is phi plus 1, therefore phi cubed is phi squared plus phi. So anyway, that's the golden ratio and how it appears in the pentagram, and I just think that's a pretty cool fact. And anyway, that concludes my video for today. So thank you for watching. Long live math, and I'll see you guys next time.